going to talk about probability again today, and this time I'm going to talk about Venn diagrams and conditional probability. So a Venn diagram can be rather useful if you want to visualize data that's already known, probability-wise, distribution-wise. And as you can see, all of these circles are enclosed by either a square or a rectangle, basically a rectangle of some kind. That rectangle, everything within that rectangle or that square represents all the possible outcomes, all the possible events. So that means that the probability or the area of that area of the square or the rectangle is 1, because the maximum probability you can have is 1. So that's why I show P equals 1 equals this, that square, that rectangle. So I'm going to introduce my key here real quick. So whenever you see an upside down U, that means and this is conventional. Whenever you see an uppercase U looking thing, except without the little line, that you'd see in lowercase, it still looks like lowercase, but it looks like uppercase, shape-wise. Whenever you see that, that means or. Whenever you see a character with a line above it, that means not, whatever it says. Whenever you see a P with parentheses and some letters inside of it, there's an expression inside of it, and that means the probability of that expression. How much area of this diagram does that take up is the best way to think about it if you're looking at Venn diagrams. So the probability of, if you have P, B, and that line, and then an A there, that means the probability of B, given that A is already known to be true. So it's like taking A and saying that A is 100% because you already know A is true. But what about how much of it is B, basically? So if we already know that A is 100%, we can ignore all the other parts of the diagram outside of A. And then now if we're going to look at B, what's the probability of B if we already know A is true? So if you want, what you would do is you would look at the area of this little lemon-shaped shape and the A circle. And then you want to take the area of the A and the B, of A and B, and divide it by the probability of A, for example, here. So, but I'm going to start right here now. So here are some important formulas that help you understand the Venn diagram, and these can be used later to make other calculations. So whenever you see A or B, whenever you want to figure out the probability of A or B, what you're trying to figure out is what is the probability of a dot. If you just take a dot on a marker and randomly put it anywhere on in this rectangle, the probability is 1 that it'll be within the rectangle if you're only putting in the rectangle somewhere. But do we know where it's going to end up in that rectangle? Well, no, we don't. If it's random, we don't know, right? So if you think about this as an event unfolding of any kind, this helps us with probability. So if you say the probability of A or B, we're saying the probability of it being in this circle or that circle somewhere, right? How do we find the total area of that, given just the area of A and the area of B? Well, there is a way to figure it out. If you notice, these circles aren't just independent circles. They're not just by themselves. They actually overlap, right? And when they overlap, you have some area that's blocked by that's covered up by the other area, right? So it's not the same thing as the area of two circles. So you can't just take pi r squared and pi r squared for A and B respectively. You have to subtract the area in the middle because that is 2 layers. You have to have 1 layer the whole way through this rectangle. So to find the actual probability of having A or B, you add the probability of A to the probability of B, and then you take and you subtract the probability of A and B. Because that's two layers there. We got to get rid of one of the layers because they're overlapping. So that is what we do here. We take the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. To figure out the probability of not A and not B, you would take 1 minus the probability of A or B. If you think about it, this is logical. So looking at the Venn diagram, the probability of not A and not B is everything outside of those circles, but within the rectangle. So that's all this area here around it. To find the area of that, the quickest way is to subtract the whole area of the rectangle. Subtract the area within these two circles that are overlapped. Whatever this is here, you subtract that from the whole rectangle. That's how you would find it, right? So when you do that, we take 1 minus the probability of A or B, which we just found up here. If we want to find the probability that B is true, given that we know that A is true, which is this right here, because we know that A is 100% somehow. We already know that A happened. What's the probability that B also happened? Well, you're looking at just the circle A. And I just mentioned this, but you take this area here and you divide it by this whole area here. So we're taking the probability of A and B, which is this area here, and we're dividing by the whole probability of A. That's how you find it. Let's say we want to find the probability of the probability of B. We could also think of it as the total probability of B. So let's say that we know the probability of B and A, which is this part here, and we also know the probability of B and not A. So let's say we know the probability of this area here and the probability of this area here. We can add those together and we can get the full circle for B. That's what that really means. Now I know it seems really simple and obvious here, but this helps when you're trying to figure things out and you only know certain pieces of information. If you know these two pieces of information, you can figure out what the probability of B altogether is. So I just went over two circles in a Venn diagram, and I explained that you got to think about the layers of the area of the rectangle, the circles, and the overlap, and only one single layer can exist over the whole area. Otherwise, this is dubious because you're hiding some of the area. So, and it wouldn't make any sense. This is already trying to represent probability, so you have to actually subtract that overlap. Now, when you move on to three circles, you have different overlap than you have here. But if you break it down, which I'll get into a little bit in a little bit, you still have the A and the B that we already went over here. So you just have to make some modifications and you can still find the probability of the three circles, just this area of the three circles, within the probability scheme within that rectangle. And I'll talk about that in a little bit. But first, let's practice actually using the Venn diagram and knowing what these probabilities correspond to. So what is the probability of A and B and C? And I put numbers here this time so we can actually find the answer. So the probability of A and B and C is wherever A and B and C overlap. A is a circle, B is a circle, C is a circle. Where do they all overlap together? Well, they overlap in the middle here. So the answer to this is 1.5. 1.5%. I show it right there. What about the probability of not A and B and C? So we got to find an area where it's not within A, but it is within B and C. So can you find that? And if you want to pause this, go ahead. But what it is it's 6%, because that's the area encompassed by C and B, but not A. So we would put 6% here. What about the probability of A and B? Well, in this, we got to look at the A and we got to look at the B. Where's the area? Where's this area here? Well, that would be this area right here. What percent is that? Well, what do we got to do? We got to do addition, right? So we got to add the 4.5 and the 1.5. What do we get? Well, we get 6% when we do that. So it's 6%. What about the probability of A or B or C? Remember, this is actual upside U. So these other ones that are and, they're upside down U's. So we're asking, what's the probability of it being A or B or C? Within this being the probability of 1, the whole rectangle. Well, this is a little more complicated, and it's like finding the probability of A or B. You got to get rid of the overlap, right? So where do we overlap and how much do we overlap in this figure? So first of all, we can say, well, we're overlapping 3 times in the very middle because we have 3 circles intersecting, right? We want to bring that down to just 1 layer. And then here, where we just have 2 overlapping, we got to get rid of this part, and we got to get rid of this part here where we just have the 2, because that's 2 layers. We got to have 1 layer here, and we also got to have 1 layer here between A and C. Well, if we just use this formula here, we already know we only have 1 layer here. So if we start out with, and let's do that, let's go, actually I don't want to quite write that yet, unless we put a large gap in there. So we have A and B, and then we subtract A and B. That's the area, if you just look at the blue circle and the red circle, that's what we have for the correct area. But since we put C here, if you look at it, we're also adding another layer to this again, right? So we already have 1 extra layer in this point right here. Even if we're using this formula, we're going to have to subtract implicitly there, somehow at least, right? If we want to add all these together, let's try to this format. Let's go the probability of A plus the probability of B plus the probability of C. Now we have 3 circles, but they're not overlapping. Just imagine the area of 3 circles without them overlapping. That's what we've done so far. Now we got to subtract out the overlap. Or we have to subtract more, but then add some back. And that's what we actually do. So one of the easiest ways to look at this is, first, just take this amount, because ignoring C, we still have this formula here. So let's subtract the probability of A and B. So we do that, we have this formula plus the area of that circle, but we still have the 2 overlaps here and on each of these, and then we have 2 overlaps here now, right? So what do? Well, how about we just subtract this lemon and that lemon there? What will happen though is we'll end up taking 2 of these away. We already had 2 of them, so we don't even have a layer here when we do that. So we're going to have to add it back though. We're going to have to add this part back after we subtract these 2 lemons, because we've taken all the areas away for this middle part. So we can go minus the probability of A and C minus the probability of C and B plus the probability of A and B. If we do that, we get the correct answer. That's how we find the area of this area with the 3 circles. So we've subtracted out all the lemons, but that left us with nothing in the middle. So we had to add them out in the middle back. And that's the formula for finding this. But if we do that, what do we end up with? So we add 20 plus 30 plus 25, that's 75. Then we subtract, let's start with this. Subtract 6 from 75, and that's 69. Subtract 5, because 1.5 and 3.5 is 5. Subtract 5 from 69, that's 64. Subtract 6 and 1.5, which is 7.5. Subtract 7.5 from 64, and we get 56.5. Now we got to add 1.5 to 65.5, and that's 58. So we should get 58% for the total area of these. So I ran out of space here, so we'll just put 58 right here. 58 is our answer. Now, what if we want to find the area of A and B and C? I'm sorry, not A, not B, and not C. How do we do that? So we're saying that it's not within the circles at all, right? It's all outside of the circles. We already found the area within the circles, just above it, right? Just right here. So if we took 1, which is the whole area of this, and we subtract what we just found, that 58, we would get 42. And that is the correct answer, 42. And I want you to pay attention to this. I've gone through the circles here, right? Now, there's the concept of independent and dependent probabilities. So if you have an independent probability, that means that two different events can happen, but when one event happens, it doesn't affect the probability of the other event occurring. Even if the other one occurred, it doesn't matter. Notice this is conditional here, when we said this is conditional. It's possible though that conditional will just give you the same probability of having the next event again by itself. If it does that, then that means it's an independent event. They're independent of each other. If it's more or if it's less than that, that means that the other event affects the probability of the next event occurring. So, if we look at this, let's look at A and let's look at B. That's 20%, 30%, right? If we wanted to figure out the probability of them occurring if they don't affect each other, what number would we expect? We'd have to multiply them times each other to find the probability of the two events occurring, and then see if it really ends up being this part in the middle, this part right here. So if we take 20% times 30%, we end up with 6%, right? So 0.2 times 0.3 is 0.06. When we do that, how does that compare to 4.5 plus 1.5, this middle part? Well, that's also 6%. So we can say that A and B are independent of each other. What about for C? So let's look at C and A, for example. 25.25 times 0.2. 0.2 is the same thing as 1/5, right? So what's 1/5 of 25%? That's 5%, right? So 5%, let's compare 5% to 3.5 plus 1.5. Well, that's also 5%. So we can also say that A and C are independent of each other. One can occur, and it doesn't matter. The probability of having this area here be also C is the same as if we didn't care about A. What about B and C? So 0.25 and 0.3. Let's take 1/4, because 25% is 1/4 of 30%. Well, 1/2 of 30% is 15, and 1/2 of that, because we're doing 1/4, is 7.5. What's this area? 1.5 plus 6? That is 7.5. So you can say that these are independent events. If they were dependent, we could still use the Venn diagram, because that's why the Venn diagram is so important. But I'm just pointing out here that we can use a Venn diagram either way. And if we don't know, we can start out with a Venn diagram, and we can still figure things out that way if you need to visualize it this way. And if you remember, it's very easy to derive these equations when using a Venn diagram. So I hope this has helped you. And that's what I'm saying over here. I'm saying that if the probability of A and B does not equal the probability of A times the probability of B, which we did find is the case here, but if it isn't, then we know that those events are dependent. Okay? I hope that this helped you. Thank you.